Okay, welcome to Thinking Beyond. This is our last webinar for this semester, but we will start up again in the fall. So look out for social media posts and emails with details probably mid-August. And if you have any questions during tonight's presentation, you can submit them at any time using the Q&A feature at the bottom of your screen, and we will get to those towards the end of the hour. That's all I have for tonight, so I will turn it over to the moderator for the evening, Maulik Parikh.
All right, thank you, Jessica. Can everyone hear me? So I'm very happy to, well, first of all, welcome everyone to this evening's Thinking Beyond. It's the last of our semester, and we're very happy today to have Dr. Mark Jackson. And Mark and I go back a long, long way. So Mark received his bachelor's in physics and mathematics from Duke University. And then he did his PhD in theoretical physics from Columbia University in New York. And we were in the same group together. And so I've known him since his doctoral days, a long time ago. And he did his PhD with his advisor was Brian Greene, who was here not too long, a few weeks ago at ASU. Mark then spent 10 years studying superstring theory and cosmology and co-authored almost 40 scientific papers. He's now adjunct faculty at Singularity University, and he's also a director of Astronomers Without Borders. But his official title is Senior Quantum Evangelist at Quantinuum. That's a quantum computing company that was originally a startup but has grown and grown, and Mark has been there for a long time. So he's now the Senior Quantum Evangelist. That sounds like somebody who might be in charge of the wave function of the universe. And so we're very happy to have him tell us today about the race for quantum computing, and he's right in the midst of all of that. So welcome, Mark.
Thank you very much. Thank you, Jessica, Maulik, and Paul. It's wonderful to be here. I've actually visited ASU many, many times, both to visit Maulik and also for possible collaborations with our company. I'm excited to be telling you things about quantum computing because every time I talk about this, it changes. The field is developing so rapidly that this presentation tonight is very different from what I would have said just a few months ago. And I first want to give just a very brief history of the company because I think it's very interesting how quantum computing companies come about. It was actually a result of Stephen Hawking, believe it or not. My boss, Ilyas Khan, was the first chairman of the Hawking Foundation. And 10 years ago, in the summer of 2014, Stephen Hawking told Ilyas, I think quantum computing is really going to take off. I think you should get into this business. And fortunately, Ilyas listened to him and founded what was called Cambridge Quantum Computing. And it was a small startup. We had an office in the Union Building at Cambridge. And I hope you all know I'm referring to Cambridge, England. And about 3 years later, they had about 30 people, all scientists, and they decided they wanted to hire an American to start to do business development and see if they could get some customers. And a mutual friend put me in touch with Ilyas, and so that's how I joined the company. As Maulik mentioned, my background is in string theory, not quantum computing, so I sort of had to pick this up on the street, but fortunately, sort of being on the business side of the company, I can't do that much damage. My title is actually Quantum Evangelist. I didn't know this until I was given this title a few years ago, but in Greek, evangelist means bringer of the good news, which is why it was originally used in a religious context. But in the tech world, it's become a pretty standard term, actually. They just want to remove it from sales because I'm not really trying to sell anything. I don't have a quota or get a commission or anything. It's really just about creating awareness and excitement about quantum computing in general, and then about what we're doing at Quantinuum. And so why don't I go ahead and share my slides here. So the format I had planned for tonight is I have some slides to talk about what quantum computing is and the history and what it can do for you. But then I hope we can save time just for discussion and answering any questions that you might have. And I'm always available to answer questions by email. So if I forget to put my email in the chat later on, please get in touch with Maulik or Paul, and they know how to get a hold of me, and I'd be glad to respond to any questions that you might have. This is a very exciting time. I actually think that 2024 will be the year of quantum computing really pivoting from what some perceive as an experimental technology to an applied technology. And last year began with a cover story on Time, which you might have seen, and it ended with a 60 Minutes feature about quantum computing. And so if there's one thing that I really want to convey, it's that quantum computing is not just a theoretical science that people have kind of dreamed up and it might be useful in 20 years. What I want to convey tonight is really that quantum computing is here and it's being used to solve some practical problems. So the way that this began, actually going back about 200 years ago to the very first computer, this was built by Charles Babbage, and he called it a difference engine in Cambridge, England. And it looks like an old-fashioned typewriter, but it actually has all the ingredients that we would identify in a computer today, because it has input devices and output devices, and most importantly, it has switches. Of course, here the switches are mechanical switches, but they're either on or off. And in 200 years, we've obviously made a lot of progress. This is a picture of the laptop that I'm giving the presentation on right now. And it's obviously a lot more powerful, it's more stylish, it's easier to use, it's incomparably faster, but conceptually it's identical because it still uses switches. In this case, of course, the switches are called transistors, and they're much smaller and faster. But the core idea here is that computers have not conceptually advanced in 200 years. And what I'll be talking about today with quantum computing represents really the first advance in how humans do calculations and think about data. The idea for a quantum computer began about 40 years ago. It was actually Richard Feynman, and I'm sure that you've heard about him and some of his colorful stories. And he was thinking about certain problems, especially chemistry problems. Because in chemistry, we've known for about 100 years what the equations are to figure out the chemical properties of a molecule. But solving those equations is very, very difficult. And Feynman was thinking about this, and he realized that even though computers get better every year, they will never become powerful enough that they could efficiently solve these type of chemistry calculations. And so in his unique, inimitable way, this quote here, it describes his thought process that if we want to simulate how nature works, we should build a computer based on that principle, which is quantum physics. And this was a wonderful idea, but 40 years ago, no one knew how to actually do this. It really was just an idea that Feynman pointed out. So what does it mean to be a quantum computer? So first, just to review, the way that normal computers work is with bits, which are binary digits. They're either 0 or 1. And you could think of this sort of like a coin on a table, and that it's going to be heads or tails. It's one or the other, and that's it. But a quantum computer uses quantum bits, or qubits, we sometimes call them. And a qubit is like that coin, but spinning in space. So it could happen to be heads, or it could happen to be tails, but it's actually free to move anywhere in between. It can rotate in any direction. And so if you were viewing it from the side, you might sort of say, oh, it's sort of heads and tails at the same time. And so it's exactly like that with a qubit. It could be a 0 or a 1, but it's free to be some combination of those two. And the technical name for this in physics is called superposition. And so this is an idea from quantum physics. When you combine this with another idea from quantum physics called entanglement, which is the idea that this qubit over here is correlated with the value of this qubit over here, even if we don't know what they are, the fact that they're correlated is an idea specific to quantum physics. When you add this idea to quantum computing, you can unlock a huge number of states or configurations that could be represented simultaneously. And so this is why we're so excited about quantum computing, is that it can solve problems which never could have been solved before by considering many, many different possibilities all at once. So going back to this problem that Feynman was thinking about, chemistry. So on the upper left-hand corner, this is my favorite molecule. This is caffeine. It's not an especially large molecule. It's only 24 atoms. As I said before, we know exactly what the equations are for trying to figure out the properties of this molecule. And we could go ahead and put that on a computer, but to solve those equations, it would need to be a very big computer. it would need to be almost the size of the planet. Now, if we were to consider a larger molecule like penicillin, again, we know exactly what the equations are, but now the computer would be the size of the observable universe. So even in principle, we could never build a computer that big, of course. Now, in contrast, it's only a very modest requirement for the number of qubits that a quantum computer would need to solve this. It's only a few hundred qubits, and I'll be talking more about how these qubits scale very soon. And so this is why we're so excited about quantum. It's not just a faster computer like the iPhone 8 compared to the iPhone 7 or something. It's a completely different way of calculating, which should allow us to solve some types of problems much, much faster, so much faster that they would have been impossible otherwise. That is one example that I've just shown you in chemistry, but it's actually many areas of science and technology that will be revolutionized by this. So there's quantum simulation, communication, algorithms, chemistry, machine learning, and I'll talk about a few of these. I could spend weeks talking about all these different areas. I'm not going to be able to talk about quantum sensing, for example, and I'll only briefly talk about quantum communication. So about 10 years ago, there were the first commercial companies, and this was a direct result because it was about 10 years ago, there were some breakthroughs. After 30 years of academic work, they had some breakthroughs that made them realize this might actually work. It might be feasible to actually make these quantum computers to solve problems that are of interest to people. And so this slide shows the entire quantum ecosystem 10 years ago. And you see Cambridge Quantum Computing, the one that I started working for. You'll obviously recognize a few of the big names like Google and IBM and Honeywell and such. I forgot to put Microsoft, of course. There's a few other names that you might not recognize. Those were a few startups in quantum. In just a few years, there was actually a big breakthrough. So 10 years ago was the very beginning, but in the fall of 2019, there was a breakthrough, and it was by Google, and it was what's called quantum supremacy. And I know that sounds very sinister. It's not as bad as it might sound. What it means is that Google found an example of something that a quantum computer could do that a normal computer could not do in any reasonable amount of time. And by their own admission, it was a bit of a silly example, but the fact that they found one thing at least was actually a big leap. I had been in the industry about 2 years, and I noticed there was a big shift in people's opinion about quantum computing. So people started to take this much more seriously, and the field really exploded after that. This is a subsection of the commercial quantum ecosystem right now. This is not nearly everyone, but this is a small snapshot that I got from the Quantum Insider, which tracks these things. You'll recognize some of the same names, but you'll see that there's many, many companies. There's now several hundred companies in quantum. Some are trying to build quantum computers. Some are trying to build the supplies for it. Some are doing consulting. Some are, for example, financial companies, but they've created quantum groups within that company to see how quantum will affect their business plan. And so there's a huge and thriving quantum ecosystem. So how do you actually build a quantum computer? I'm going to show two examples here. So on the left-hand side, this is an example of what's called superconducting technology. And you'll recognize this golden chandelier. It was on the cover of Time that I showed in the beginning. So certain properties, when you get them, certain materials, when you get them very, very cold, they exhibit these amazing properties that they can conduct electricity almost perfectly. And a few years ago, people realized they could actually exploit this to make them quantum computers, rather. And so IBM and Google and Rigetti and a few others are using this technology. And so you see she's working on the chandelier, but in order for this to work, you have to keep it near absolute zero. And so for that reason, they actually submerge that chandelier in liquid helium. And that's why you see those white cylinders in the background there. Those are actually filled with liquid helium, and they're sealed up. So when the quantum computer is being used, it's always sealed up like that. Now, a different technology is what's called ion trap technology. And that's the example that I show on the right. And that's what we happen to use. In this case, every qubit is a charged particle, an ion, which physically moves around. And then by changing the energy values with lasers, you can represent the 0 and the 1 in different configurations and entanglements. And I have a video here from MIT, which actually shows how this works. So that glowing dot is an ion. and it's being manipulated using the lasers. So it's physically being moved around, and then it's getting its value changed between the zeros and ones. And of course, one qubit isn't very interesting. The interesting thing happens when many qubits are doing this together. And when they're being put together, that's the entanglement. So they become entangled and they move off and they become entangled with others. And so when a quantum program runs, it's actually a very sophisticated choreography of all these qubits doing their dance like this. So I mentioned two different examples of the technology. So I mentioned superconducting and I mentioned ion trap. There's many other different approaches. Every approach has advantages and disadvantages. I don't want to imply that one is correct and all the others are wrong. I think there eventually will be a place for all of these technologies in some form. I think it's just going to be that some programs are better run on different technologies or others. Since I'm seeing PsiQuantum there on the slide, I'll just mention today in the news I saw that they received almost I think it was about $620 million in US dollars in funding from the Australian government, just to give you an idea of how big the dollar amounts are of investment here. The current qubit record is currently held by IBM. They have 1,121 qubits. And that sounds astonishing. You might say, well, if we only needed a few hundred qubits to solve those chemistry problems that I showed you, if we have 1,100, doesn't that mean that we could basically solve any problem of interest? The answer is no, and it's for the following reason. The number of qubits alone is not sufficient to indicate how powerful a quantum computer is. And the reason for this is because qubits are physical objects. However you build them, whatever technology you use to build a qubit, it's a physical object, and so it doesn't always do what you want it to do. There's always some error associated with it. And different technologies have different inherent error rates. But several years ago, it dawned on different quantum groups that it wasn't just the qubit count alone. And so they actually came up with this new metric called the quantum volume. And it has nothing to do with a physical volume. It's just a term they use. But the quantum volume, it's a complicated formula, but it takes into account the number of qubits and the quality of the qubits. So the fidelity, the opposite of the error, the way that the qubits are connected, the length of time that the qubits preserve their special quantum properties. So we call this coherence time. So all these different factors that come into how powerful a quantum computer is, they all feed into this one metric called the quantum volume. And I've shown in the orange, this is how the quantum volume has advanced in the past few years. And it's actually more than a factor of 10 every year. And in contrast, I've shown there in that grayish line, that's Moore's law, which I believe most of you have probably heard of. Moore's law is how normal computers have advanced, and they've doubled in power every 18 months or so. And so you see what a faster trajectory quantum is on compared to normal computers. And it's for this reason, we actually think that we will start to see practical applications of quantum computing within a year. And I'm emphasizing this point because I can't count how many times I speak to executives or something, and they might have heard about quantum computing, but they have this misunderstanding that quantum might be relevant in 20 years. And they have no idea just how far it's advanced the past several years and how close we are to having practical applications. Right now, we're most of the quantum computers that are being used are in what's called the NISQ era. And NISQ it's a term coined by John Preskill, a professor at Caltech, who's sort of one of the grandfathers of quantum computing. And he came up with this acronym. It stands for Noisy Intermediate Scale Quantum. And the idea is that quantum computers don't have that many qubits, and they're kind of noisy in that they have a large error rate. We can't really do much about it, so we just keep our programs short and hope for the best. And until recently, that's sort of how we've had to deal with things. But very recently, we've been able to do something called quantum error correction. And quantum error correction, it's a way in which we can actually correct the mistakes by these qubits. And you might say, well, Mark, normal computers make mistakes all the time. Why don't we just correct them in the same way that normal computers do? Why do we have to think about it in a special way for quantum? let me give you a simple example. With a normal computer, you might take a bit and you just make 2 copies of it. So you have 3 copies of that bit. If one of them happens to do something wrong, that's okay, because as long as 2 of them are giving the correct answer, you can just decide to take the majority in any problem. And that's how you know what the correct answer is. As long as the probability of one of them making a mistake is very small, and that it's not too likely you would get 2 mistakes simultaneously, then that works just fine. And so it's very simple to do error correction for normal computers. But in the quantum world, it's a little more complicated because there's actually 2 reasons that you can't do what I just described for quantum computers. The first reason is that one of the rules of quantum physics says that you can't copy quantum data. You can move it around, but you can't make an exact duplicate. And so we would never be able to make those 2 copies of a qubit. And the second rule of quantum physics says that just by measuring the qubit, you've actually destroyed some of the information. We say that you've collapsed the wave function. And so by measuring the qubit to identify whether an error happened, you've actually destroyed the information that you were trying to preserve and use in future calculations. And so for that reason, it actually took a long time for people to figure out how to do quantum error correction, because it's much more subtle. It turns out you can do it, and the way that you do it is by spreading the information of one qubit over several qubits. And there's different ways to do this, and it's very mathematically complex, but there is a way to do it. The caveat, though, is that in order for this to work, the error rate has to be really small to begin with, because otherwise adding more qubits in order to do the spreading actually makes the problem worse. And so it was only very recently that we were able to do this so-called quantum error correction in a way that actually helped things. It was actually only last month that we were able to do this. And this was a big announcement. I would encourage you to Google this. It was actually the Microsoft team that did this using our quantum computer. They used 30 of our qubits on our machine and using quantum error correction. So they actually had the information corresponding to 4 qubits, but they smeared it over 30. And then by doing this and using quantum error correction, they were able to decrease the error rate by a factor of 800. And just a few years ago, this would have been inconceivable. We never would have been able to do this until recently. And so now, actually, for the first time, we can actually do calculations reliably. They were actually able to do, I think, 17,000 runs of their program without getting a single uncorrected error. And again, just a few years ago, that would have been impossible. And so this is just a month ago that this happened. So we really are starting to see some big breakthroughs in how practical quantum computing is. So now that we know that the technology is getting better, what would you actually do with it? So before I tell you the applications, I want to show you, this is what a quantum program looks like. And I know this looks kind of silly. It's completely different from what a normal computer program looks like. It looks like some sort of child's game or something. But this is actually what a quantum program looks like. The way that you would interpret this is that every horizontal line there is a qubit, and you read it from left to right. So on the left-hand side, so this corresponds to 4 qubits. On the left-hand side, each of the qubits is getting initialized to the 0 configuration, so we know where it begins. And then those colored blocks are transforming the qubits. So those blue colored blocks, each of them is acting just on that one qubit that it's sitting on top of, and it's rotating the qubit, so it's changing the value. And then you see some of them are coupling 2 qubits to each other. That's the entanglement. So it's saying, change the value of one qubit depending on what the value of the other qubit is, even though I don't know what it is. And so you have all of these different operations. And then at the very end, you have the measurement operators. And so up until the very end, the qubits are in states of superposition and entanglement and such. But then at the end, when you measure the qubits, the only answer that you will get for each qubit is 0 or 1. So the output is purely digital. You never get to peek inside and see the different superpositions and such. All you have is the output, which is digital. The quantum program itself is all of those operations in between. So every quantum program has this type of form. So what would you do with this? So I've already mentioned chemistry is one of the big applications. And of course, chemistry is very, very important to material science and to the pharmaceutical industry. In the industrial world, there's all sorts of logistics and scheduling and planning associated with that, and you're always trying to optimize this and make things as efficient as possible. In the finance world and in the IT world, there's all sorts of machine learning applications, and I'll talk some about this. And then in finance, of course, there's all sorts of trading algorithms that are being used. And so I'll mention some of these applications, and I'm mentioning all of the different companies that are already getting into quantum. So the logos that I've shown here, these are examples of companies which have publicly announced that they're already using quantum. So again, I'm really trying to emphasize this has really moved out of the laboratory and into the corporate world. So JP Morgan, for example, when they do portfolio optimization, they're always trying to optimize this and find the minimum risk or the maximum profit or something. And quantum computers are very good at this type of thing because they can consider every possibility simultaneously, and then the correct answer emerges. And so JP Morgan is trying to use quantum machine learning for this type of thing. Many different financial groups are using this for their trading algorithms. So of course, when you have a trading algorithm, you're looking at the history of things like stocks, trying to figure out the patterns so that you could place your bets accordingly to try to predict the future and benefit from this. The mathematics from all this is usually based on something called Monte Carlo simulation. And Monte Carlo, it's wonderful for dealing with systems which are so complicated that they might as well be random. There probably is some underlying basis behind this, but it might as well be random. And so the more times that you do these simulations, the more accurate a result you expect to get. It turns out that there is a quantum Monte Carlo algorithm, which is quadratically faster than the classical version. So that means that you would expect the same level of accuracy from 1,000 quantum simulations as you would from 1,000,000 classical simulations. And so obviously a lot of financial firms are very interested in this because it should be able to improve their trading strategies. Another application of quantum machine learning is in fraud detection. Unfortunately, in today's world, fraud is sort of a ubiquitous problem, and a lot of effort goes into identifying the fraudulent transactions and separating them from the legitimate ones, because of course you don't want to annoy your legitimate customers. And so it's actually believed that will be one of the big applications of quantum computing. If anyone has ever used Alexa or Siri or a chatbot, what you've actually been doing is something called natural language processing. And so NLP, as it's called, it's how computers understand how humans put words together in sentences and what we mean by this so that the computer can act on that. And there's a whole mathematical structure behind NLP. It turns out that there's a very natural quantum natural language processing. It turns out that mathematics very naturally adapts for quantum computing. And we actually have a whole team based in Oxford dedicated specifically to this. And you might ask why, of all the things we could do, why NLP? It's because we believe that this is the first step towards quantum AI. There's been a lot of attention to AI given the past year with ChatGPT and such. We believe this is actually the first step towards adding quantum to that. And so we expect in the next few years that we should be able to connect quantum with AI. So I mentioned chemistry in the very beginning of my presentation, so I want to say a few more words about that. If all you care about is kind of an order of magnitude vague estimate of how a molecule will behave, then normal computers can do that. That's fine. But as you want more and more accurate results, you see this curve shows the trade-off between the accuracy of the result that you'll get and how expensive it is computationally. And if you want what's called chemical accuracy, if you want the extreme end of that curve, that's very, very difficult. I believe right now the record is 20 electrons, not 20 atoms, 20 electrons. So you would be limited to very, very small molecules if you insisted upon that much accuracy. But quantum computers can get that level of accuracy very efficiently. And so for that reason, we're very excited about using quantum computing for different chemistry problems. And you might ask, what would be the most valuable chemistry problem to solve in the world? And you might be shocked to discover it's actually fertilizer. And that might seem oddly specific. Why would fertilizer be such an important problem? But it turns out about 2% of the world's energy supply goes into making fertilizer, and it's a horribly inefficient process. It hasn't changed much in 150 years, and it's very expensive. It's bad for the environment. It uses a lot of resources. It turns out that bacteria are much better at doing this than we are. We just don't quite know how they do it. It has something to do with this reaction that I'm showing here on the screen. It's called FOMOCO. If we were able to simulate this reaction, like bacteria, we think that we would be able to do this. We would have a synthetic version of this. And so a lot of attention has gone to being able to simulate this. Several years ago, there was an estimate that we would need 200 million qubits calculating for several months to solve this problem. And of course, that's a little depressing, but in just a few years of work, we were able to bring that down to a few million qubits calculating for 4 days. And even though that still seems out of reach, that's actually well within what we think that we'll have within a decade or so. And so we actually think we'll be able to tackle very important problems using quantum computers within a decade or so. Personally, the thing that I'm most excited about is actually how quantum computing would affect the pharmaceutical industry. I was shocked to discover that it takes a pharmaceutical company about 10 years and $1 billion to bring a drug to market. And this is because even though they use computers in the very early stages to try to identify what the most promising drugs are, they can only get vague estimates of which ones those are. And so then they have to go to clinical trials. And this is expensive and it takes a lot of time. And it's kind of risky for the people involved in those trials. And the best they could hope for is that a drug will help most people and it's not too harmful for most people. Whereas if we were to use a quantum computer, we expect that we would be able to much more quickly identify the most promising drugs and focus on those in the early stages before it ever gets to clinical trials. And so this could revolutionize the way that drugs are developed. Some of the things that we're already starting to apply quantum computing to are some of these problems. For example, Total has been using quantum computing to extract CO2 from the environment. Nippon Steel has been analyzing the metallic structure of steel. And Roche has been working on studying a potential drug for Alzheimer's and seeing how this interacts with our biology. So again, we're already starting to look towards very important real-world problems. I mentioned optimization as one of the big applications. And so, for example, Deutsche Bahn, the German rail group, they actually have used a simplified version of their schedule, and they were able to find a more efficient way to do this using quantum computing. And again, with Nippon Steel, they were able to find a more efficient supply chain process in their assembly line process. So the final thing I want to talk about is cybersecurity. And I've kind of noticed as the one thing that people know about quantum computing is that it has something to do with hacking. And there is a good reason for that. That is true. And let me explain a little bit more about that. When you communicate over the internet, what you're doing is you're having your computer encrypt your credit card numbers or whatever, any sensitive data, and that's what gets transmitted. And that encryption process is actually applying a very complicated mathematical formula to your data. The recipient, the computer on the other end, they have what's called a key or a string of numbers that they use to undo that formula to retrieve the original credit card numbers or whatever. And most of the time, this works really well. And this is because the formulas that were developed about 60 years ago to do this, they were purposely chosen to be so complicated that normal computers could not undo them in any reasonable amount of time unless they had the key. So it might take a computer like 1 million years to do it, but of course it's hardly worth doing that just to get someone's credit card numbers. So most of the time this works really well. Unfortunately, when they developed this all that time ago, they weren't thinking about quantum computing, which is understandable because no one had even conceived of such a thing. But it was about 30 years ago that it was realized that quantum computers were very good at undoing some of these types of encryption. If you're curious, it was actually quantum computers' ability to factor numbers into prime numbers, because that's the mathematical basis for a lot of types of encryption. So the top half of this screen, this shows some of the different cryptography methods which are vulnerable to quantum computing. This represents about 99% of the internet. So this is a very real threat. Now, fortunately, people have been aware of this for several years, and so they've already started to take precautions. There's actually a contest going on right now where people have been submitting ideas for new and different encryption methods, which we don't think quantum computers can hack. And I want to emphasize, we don't think, because we actually don't know. It's really an ongoing process right now. 2 years ago, there were 4 so-called winners, and then within days, 2 of them were hacked. And so it's a very new subject. In fact, actually, just last week there was a thing. Someone claimed to have hacked one of these, and then after a few days, it was discovered there was an error in their analysis. But it's still very much an active field. Last fall, Signal was the first major messaging app in which they actually incorporated one of these types of post-quantum encryption. So they've already made the move. And then a few months ago, Apple did the same thing. So if you use an iPhone right now with iMessages, it's actually getting encrypted using one of these. And so companies are already starting to protect themselves against this type of hacking. Even though it's not possible today, they want to be sure to protect the data so that in the future, if quantum computers are able to do it, they can't go back and decrypt things and read people's mail. So for these reasons, if you're in a position to do so, I would highly recommend that you upgrade today. The final thing I want to talk about is something that's not often discussed. It's actually how quantum computers can be used to protect communication. And this is something called quantum key distribution. It's where you're actually transmitting the quantum data itself. And so you usually use either fiber optics or lasers in empty space to do this. So you're actually exchanging photons, which actually have the quantum data itself. And to understand why this is such a secure method of communicating, before I show you, I just want to mention this is actually already being used. In fact, the Chinese actually have a quantum satellite called Messias, which is up in space. It's been up in space for 8 years already, and they actually use this process for this. So to explain how this works, so imagine that you had a source of entangled qubits. So these could be photons. Remember, entanglement means that you may not know what value the qubit has, but whatever it has, they're the same, right? So the 2 qubits which are entangled, they're always identical. So you first do a calibration check. And so the 2 people communicating, we'll call them Alice and Bob. Alice measures her qubits in some direction, and Bob measures his qubits in some direction. And they don't compare notes yet. They do this independently. They do this many, many times, like 1,000 times. And then, after they've done that, then they compare notes. And if they happen to measure in the same direction, they should always get the same answer because of that entanglement. If the entanglement really is there, they should always get the same result 100% of the time. But now redo that. Imagine that there's some sort of eavesdropper. So the eavesdropper is intercepting from, let's say, Bob, measuring the qubit and then replacing it. And they're trying to be sneaky. They're replacing the qubit with the result that they just measured, right? And if this were a classical physics setup, it would be the perfect crime because there would be no way to detect that eavesdropping has taken place. But this is a quantum system, and the fact that it's been measured already destroys the entanglement. And so even though the eavesdropper is trying to be sneaky, you notice that it is different. And so now when Alice and Bob do their calibration check, even if they've measured in the same direction, they don't always get the same answer. A large fraction of the time, they're going to get a different result. And so now Alice and Bob have mathematical proof that something funny is going on. Someone is eavesdropping or tampering, or the system's not working or something. And so in that case, Alice and Bob can stop communicating and shut it down and start it up somewhere else. And so that's why this is such a secure way of communicating. It's not just that it's a complicated formula that a computer can't hack. It's actually based on fundamental physics that we can do that. So we absolutely have quantum computers right now, to conclude. I think in the next year or two, we will start to see the first practical commercial applications where they really do useful things. I think within about 7 years, they will be fully integrated. I think we will have quantum computers and GPUs and normal computers all working together. In terms of the cryptography and such, we are developing these so-called post-quantum encryption algorithms right now. In 2 years, it might be possible for a quantum computer to do it, but I think within 7 years, it's actually likely. And so again, if you're in a position to do so, I would recommend that you upgrade already. And so, so that is it for my prepared presentation, but I'm happy to chat and answer any questions that you might have.
Thank you, Mark, for that fascinating talk. I want to let everyone know that we have a Q&A box at the bottom of your screen, so please go ahead and enter your questions. Before we get to those questions, Paul, did you want to say something?
Well, yeah, wonderful talk, Mark. Yeah, I love it. And a few things were going through my mind. This intersection of the world of computing and the world of finance led to something everybody knows about, Bitcoin. Are we going to have Bitcoin? Is it going to change that whole landscape?
Absolutely. In fact, this is one of the most common questions I get asked. Could you use a quantum computer to mine all the Bitcoin? And so there's actually two parts to the answer. If you're asking, could you use a quantum computer to actually do the mining itself? The answer is no. There was a study done on exactly this question, and it turns out that the mining algorithm is not efficient on a quantum computer. And so that answer is no. Could you use a quantum computer to hack Bitcoin if the cryptography is of the old type? And the answer is yes. You could actually steal it from someone else. And so for that reason, absolutely, all of cryptocurrency and blockchain and such will need to be upgraded in their security systems.
So the other thing is that at the end of the talk, you were talking about transmitting qubits, optical fibers up into space and so on. And so this is the beginning of quantum internet. And I think we all understand the power of the computers that we have at hand, like the one I'm talking to you on at the moment, is we can network them. And so we could distribute problems and calculations all around the world. People are talking about developing a quantum internet. Is it going anywhere?
It is, absolutely. So there absolutely will be a quantum internet. It will not replace the existing internet, but it will augment it. So we will still need digital communication, but we will have to have a quantum component. The average person would not have a quantum internet, but governments and financial firms and communications companies would, because they're the ones who have large amounts of data that really needs to be kept secure. And so they would do this. And there are places which have small localized quantum networks. So for example, I know in the UK, they have one, in Switzerland, in South Korea. I heard that like some hedge funds did this out on Long Island, near where I am. China is very, very interested in quantum communication. And so I have no doubt that they will be doing this as well. So yes, we absolutely will have a quantum internet.
I have one last question of a more philosophical nature, and then we'll turn it over to the audience. It's often said that every bit of human technology, nature got there first, and we tend to think that in biology. Is quantum computing the only technology at last that humans have invented that nature isn't doing, or is nature sneakily doing quantum computing?
It absolutely is nature. That was I've never heard that quote, but that's absolutely true. No, the whole Feynman's great insight was, we're very bad at building computers. Nature is so much better at this. We should try to emulate the way that nature calculates. And so that's why we building these computers to try to do the calculations in a way that nature does. When molecules are constructed, it's all based on quantum physics. And so we're trying to mimic that.
You don't think that biological organisms are manipulating qubits?
You're referring to things like having
quantum biology.
Quantum biology. Most of the time I would say no. I don't see how that's possible, but I actually have heard of very legitimate groups doing research on this, thinking like for example, the way that some animals sense magnetic fields. So I actually have heard of legitimate work in this area. I just don't know anything about it.
I'm going to be quiet now and let Maulik moderate the questions.
Right. We have lots and lots of questions, which is not surprising given your provocative talk. So let's start with a question that was sent by email by Barbara Temple, and there are also a similar question, I think, by Drake Pry, which was basically, will we be able to create a quantum computer that functions at room temperature? Are we going to have quantum computers, that you can buy at the Apple Store, or is this just going to be something that requires, a lot of
liquid helium? No, so the answer is absolutely. In fact, the technology that we at Quantinuum use, the ion trap technology, one of its big advantages is that it will work at room temperature. Right now, we do cool it, not with liquid helium, but we keep it cold because it helps. But eventually, we will be able to put this on an integrated chip, like other types of computers. Another example is the photonic approach I mentioned, like PsiQuantum and Xanadu. That works at room temperature. They print it on a chip automatically. And so it's entirely possible that, not tomorrow, but maybe in 10 years or so, that you will be able to have a quantum computer on an iPhone or a laptop or something, that it will be available for personal and portable use.
Wow. So related to that, Gil Spire asks, what is the current progress in topological quantum computing?
Excellent question.
Maybe you should also say what topological quantum.
I'll explain what that is. So one of the approaches, I didn't show this in my slides here, it's what's called topological. And this actually started a brilliant physicist named Frank Wilczek, who later went on to win the Nobel Prize. And I believe that he's no stranger to you at Arizona State, and was also Maulik's PhD advisor. He was thinking about particles in nature and how in the real world, we only have bosons and fermions. And one of the characteristics of these is that the fermion changes sign when you move them around each other. And Wilczek realized that in lower dimensions, in only 2 dimensions, there's a lot more possibilities that the wave function could change by anything if you limit yourself to that. And so he called these potential particles anyons. And it wasn't much longer than that. A professor now at Caltech named Kitev, he realized that this would be extraordinary for quantum computing, because if these particles, if they only cared about big movements, like how they moved around each other, there would be almost 0 error, because any little jiggles would basically be irrelevant. And so you could have sort of a braiding pattern and encode information like this. And so, so that's why they're called non-abelian anyons. They have a structure in this braiding. And there was a company that tried to build these non-abelian anyons directly using Majorana fermions. So this is another hypothetical particle which should have these properties. And they made a lot of progress, but then they realized they had misinterpreted some data. And so they had to retract some of their statements. And so I don't quite know what the status of that is. I didn't talk about it in my talk, but since you're asking, last year we were actually able to do this on our machine. So even though we don't use Majorana fermions, we were able to use our machine to do the same thing. Using our qubits, we were able to build these non-abelian anyons for the first time and exhibit this type of braiding pattern. And this was a major result. No one had ever done this ever before. And so there was a lot of coverage, and Wilczek was interviewed and gave it his blessing. So that's the status. I don't anticipate anyone using Majorana fermions anytime soon, but we're actually able to do this using our machine already.
Okay, great. Jim Masessa asked for a little clarification. It says, in your example, how did the 4 qubits, the 4 logical qubits, divide among the 30 physical qubits, since that isn't even an even distribution?
That's absolutely true. So what happens, as I said, it's a very clever way that you smear the information of one over several. And it's done in a very subtle way, such that you can't point to this goes here. It really is smeared in a very clever way. And I'm afraid I can't really be more descriptive without using math about that. But actually, quantum error correction is probably my favorite subject within quantum computing, because it actually has connections with my previous career in string theory, in the sense that we're starting to understand how nature encodes quantum information. And so we're learning how to do it in a very crude way, but somehow nature does it in a very clever way. And the name of this is called holography, maybe not in the hologram sense that you might have heard of from Star Wars or something, but somehow nature does very cleverly encode quantum information. And so we're beginning to understand how to do that. And so yeah, it's basically one perfect qubit, we call it a logical qubit, is smeared over about 7.5 physical qubits.
Okay. Drake Pry asks, can you elaborate a bit on AI and quantum computing?
Absolutely. When people talk about AI, what they really mean is machine learning. And machine learning, even really sophisticated machine learning, at its core, normal machine learning is just based on probabilities. And of course, a probability is a number between 0 and 1, whereas quantum AI would depend on quantum machine learning, which does not depend on probabilities. It depends on something called an amplitude or a vector. And recall that the difference is that an amplitude or vector has a direction associated with it. And so if I add two probabilities together, the only way that I can get 0 is if both of those probabilities were 0 to begin with. Whereas I could add two amplitudes or vectors together and I can get 0, even if neither of them were 0 to begin with. And so the mathematics of quantum AI will be much more sophisticated than normal AI. I heard someone say that quantum AI will make today's AI look like an abacus. It will look so elementary. There's a lot more nuance, and we actually think this is the beginning of getting computers to actually think and understand. I know that sounds very science fiction-y, but that's where we think that this will head in a few years.
So related to that, Derek Youngson asks, great talk, thank you. Will quantum computing solve the theory of everything and the unification of the laws of physics, since after all, they're going to think?
I would love that conclusion. As someone who went into string theory, hoping to have answers to all of these things, I would love that. I don't want to promise that, but the example that I just gave of connecting quantum computing using holography is something that I'm very excited about, that maybe quantum computing could give us some insights of why the laws of physics are what they are.
Okay, so there's an anonymous attendee is skeptical of your what he calls it, or she calls the rather optimistic view to the future of quantum computing based on previous results. How do you know that your extrapolation is accurate or realistic for the future? There's nothing that proves that there are no barriers to the future of scaling or entanglement, so it seems overly optimistic.
No, that's a very good question. And when I'm actually very happy they made that comment. When I started in this field about 7 years ago, many of my physics friends, not you, Maulik, but many of my physics friends were very skeptical. They said almost exactly those words. Why do you think this is going to go anywhere? It seems like there's a lot of challenges and assumptions and such. And I wouldn't say that I was skeptical, but I think I had reason to be cautious 7 years ago. But there's been so much progress since then. It's really no longer an issue of the physics. It's really just engineering, because it does work. We have it working all the time now. We routinely run quantum programs all the time now. I also know what we have in store. I know what our research teams are working on, and they've already done some amazing things, which the public won't hear about for a few years. And so I think we've already demonstrated that it works in principle. It's really just now a matter of scaling up. And I can't prove that in a few years, maybe we'll find some barrier to that will prevent us from scaling up as much as we want. But we're truly not aware of any such issue right now. We are very optimistic. Okay.
You mentioned it several times that about how we should protect ourselves from hacking of classical cryptography. And so Daniel Simmons wants to know specifically how do we upgrade our computers and what do we need to do?
Sure. So it would really be your security person, whoever takes care of email security, or your sysop or whoever. They would be the ones in charge. They would have to install new cybersecurity software for the encryption. So the individual user would not be able to do that.
I see. Okay. Michael Thorpe asks, what is the largest product of 2 primes that has been factorized using a quantum computer? So this is a classic problem in the classical computer.
I don't know the answer. And the reason I don't know is because we don't use our quantum computers for that reason. So if I knew the answer, that would be suspicious.
Okay. Let's see. David Bueller says, exciting. Have in the US, are there national leaders in government been sent to a boot camp training that looks at the implications of quantum computing for privacy, surveillance, etc.? Or did the mind-spinning world of AI get to them first?
The government is aware of it. Different governments are doing different things and are at different levels. I would say the UK government was one of the first in this. The Finnish government was one of the firsts. So several European governments were into this. The Chinese are basically writing blank checks. They're very, very invested in this. In China, of course, there's a much closer connection between government, military, and the private sector. So those are much closer involved. The US is supportive of this. They are supporting it to some degree. It's mainly the private sector. We are surprised, though. So we work closely with all of the government agencies that you would imagine, and it is surprising how little they know about the current state of quantum. They seem, it seems like the information they have is based on several years ago, and I think they do need to get updated a bit.
Okay. Right, here's another question. This is from Kartavya Chauhan. Can quantum communications be used in longer space missions? For instance, can qubits inside photons be used to send information on large distances?
Yeah, so the answer is yes. What happens, though, is that the longer the distance, the less the chance that the photon makes it there. And so that's why, like right now, I mentioned that Chinese quantum satellite, that's just in orbit around us, right? And so it's, you know, it's longer than like 2 cities or something, but it's not like deep space. It would be difficult to use even lasers for deep space communication for quantum, because it needs to be so precise. You need to have the photon not just get there, but retain the same polarization and properties and everything. And so that would be very difficult to have a quantum link over very long distances.
Okay. Another sort of a pragmatic question by Drake again. Can you talk about if programs need to be written different to run on quantum computers versus classical? I mean, what is the programming languages? How does one actually write a code?
Very good question. Yeah, it's completely different. It needs to be completely rewritten. We only have very few quantum algorithms at present. You would actually be shocked. All of the software we run right now is based on just a handful of quantum algorithms. In fact, I've basically mentioned all of them that we have. So we know how to factor numbers. That's the hacking one, unfortunately. We know a few different machine learning algorithms like quantum Monte Carlo. We know a few different optimization ones. We know chemistry. We know how to simulate different molecules. That's about it right now, actually. And it's because quantum logic is so counterintuitive for humans. It's just not at all what we're used to. Just to give you one quick example, normal computer programs are really just a sophisticated set of if-then statements. If something's true, do this. If it's not, do something else. And a program is really just a complicated series of that. But of course, with a quantum program, it can be sort of true and sort of not at the same time if it's in the superposition of 0 and 1. So which fork do you follow? So for that reason, quantum programs are completely different from normal programs. Oh, and you asked which language. There are several different languages, but they're all very similar. All of them are basically just manipulating those qubits to do different operations and then measuring them. So they're just different versions of that.
Can you name a few of those, or?
Sure, I'm happy to. So the most popular one is by IBM. It's called Qiskit. There's Cirq by Google. There's Q-Sharp by Microsoft. We have one called Ticket, T-K-E-T. Yeah, so they're all very similar.
And can ordinary users learn these languages and write things that run on run on their computers?
You would need some training in quantum physics, because you would need to understand what a qubit is and what entanglement is and why to do these things and how to get a result based on this. And so it takes quite a bit more work than just like Python programming.
Right. Okay. Well, we're actually out of time. The questions are still streaming in. Mark,
I put my email in the chat there, mark.jackson@continuum. So please email them to me and I'd be glad to answer them all.
okay, great. Thank you very much. And we'll see everybody next year, or next academic year rather, with the next our upcoming season of Thinking Beyond. And thank you all for attending these.
Thank you all so much.